In August 1945, a squadron of Navy fighters sailed toward the Pacific to save the fleet from kamikaze attacks. Before they fired a single shot, the atomic bombs fell and Japan surrendered. This is the backward story of the fastest climbing propeller fighter America ever built. A machine engineered with obsessive genius for one mission: it would never, ever get to fly. Chapter 1. The war that ended without them. Start here, because this is the moment the entire story secretly hinges on. August 1945, somewhere in the Pacific, the aircraft carrier deck crews of Fighter Squadron VF-19 are going through their final workups, preparing to join the fleet for what everyone assumes will be the bloodiest phase of the war yet: the invasion of the Japanese home islands. Below deck sits a fighter unlike anything the Navy has fielded before: small, brutally powerful, capable of climbing to altitude faster than almost anything else, with a propeller on the front of it. It was built for exactly this moment. It was built to solve exactly this problem: getting into the air fast enough to shoot down a kamikaze before it reaches the ships. And then, before a single one of these fighters fires a shot in anger, the news arrives. Atomic bombs have fallen on Hiroshima and Nagasaki. Japan is surrendering. The war that this aircraft was designed, tested, rushed into production, and shipped across an ocean to fight in, is simply over. Here's the paradox we're going to unpack today. The United States Navy built what may be the single most perfectly optimized, propeller-driven interceptor of the entire Second World War. An aircraft engineered from the ground up around one obsessive design philosophy, rushed through development in barely 2 years, and it never once fired its guns at the enemy it was created to kill. Its combat record against the Japanese Empire is exactly 0 missions, 0 engagements, 0 kills. And yet, decades later, this same aircraft would be called the favorite plane ever flown by the first human being to walk on the moon. This is the story of the Grumman F8F Bearcat, the fighter that arrived one war too late, got humiliated by the jet age within months of finally entering service, was handed off to fight a war it was never designed for, and only found its true glory on a desert racetrack in Nevada, decades after anyone in the Navy still cared what it could do. To understand how an aircraft this good ends up with a combat record this empty, we have to rewind, past the surrender, past the shakedown cruise, past the factory floor, all the way back to a single blunt question asked to a group of exhausted fighter pilots, 19 days after one of the most important naval battles in American history. Chapter 2: The problem no one had solved yet. Rewind to the summer of 1942. The war in the Pacific is still desperately uncertain. American carrier pilots flying the Grumman F8F Wildcat have just fought the Imperial Japanese Navy to a decisive standstill at the Battle of Midway, but every pilot who survives those dogfights comes home with the same uncomfortable admission: their aircraft is simply outclassed, plane for plane, by the Mitsubishi Zero. The Zero climbs faster, it turns tighter, it outmaneuvers the Wildcat in almost every engagement that isn't fought purely on American discipline, teamwork, and tactics like Jimmy Thacke's now famous Thatch Weave. The Navy already has an answer in the pipeline: the Grumman F6F Hellcat, a bigger, more powerful fighter specifically designed to outmuscle the Zero rather than outturn it. And within a year, the Hellcat will indeed become the dominant American carrier fighter of the war, racking up a kill ratio against Japanese aircraft that will go down as one of the most lopsided in aviation history. The gap wasn't subtle. Zero pilots could outclimb a Wildcat by a wide enough margin that an American pilot caught below and behind a Zero in a vertical fight was, in most circumstances, already losing that fight before the first shot was fired. Thacke's own tactic, 2 fighters flying a weaving crossover pattern so that whichever pilot got jumped from behind could lure the attacker into his wingman's guns, was born specifically because American pilots needed a way to win despite their aircraft's inferior performance, not because of it. It worked brilliantly, and it would go on saving American lives for years. But it was also, fundamentally, a workaround. a tactic invented to compensate for a machine that could not yet win on raw performance alone. But even before the Hellcat has proven itself, naval planners are already worried about a narrower, more specialized problem the Hellcat isn't quite built to solve. As the war drags on, Japan is going to lean harder and harder on a single desperate tactic, launching waves of aircraft and eventually suicide attackers directly at the fleet. Radar can give a carrier task force some warning, but only minutes. What the fleet desperately needs is not simply a superior all-around fighter. It needs an interceptor, something small, light, and absurdly fast off the deck, capable of launching from a carrier and reaching intercept altitude before an incoming raid ever gets within striking distance of the ships it's protecting. Speed and raw rate of climb, not maneuverability, not range, not even firepower, become the only numbers that actually matter. Chapter 3, 19 days after Midway. Here is the detail that makes this story worth telling instead of just another spec sheet. Grumman's leadership didn't sit in a design office guessing what the fleet needed. Only 19 days after the guns fell silent at Midway, company engineers and executives sat down directly with combat-experienced fighter pilots, fresh off the carriers, to ask them, point blank, what the ideal fleet defense fighter of the future needed to be able to do. Among the men in that room was Lieutenant Commander Jimmy Thack, already a legend for the tactic bearing his name, and a pilot who had personally watched, in real time, exactly how badly a slower climbing American fighter could be caught out of position by a faster climbing Japanese one. Thack's answer to Grumman's question was blunt, specific, and almost defiantly simple. Climb rate, not top speed, not turning radius, not even raw firepower. The fighter that was actually going to save the fleet, he argued, wasn't necessarily going to be the fastest aircraft in level flight or the hardest hitting. It was going to be the one that got to altitude first. Because, in the specific, narrow, terrifying scenario of intercepting an inbound raid with only minutes of warning, altitude and time were the only currency that mattered. That single answer, from one experienced combat pilot speaking candidly less than 3 weeks after one of the most consequential battles of the war, became the design seed for everything that followed. Grumman's engineers didn't walk away from that meeting with a wish list of features. They walked away with a design philosophy reduced to its purest, most ruthless form. Build the smallest, lightest possible airframe you can physically wrap around the most powerful engine available, and cut away absolutely everything else that isn't essential to getting that airframe into the sky as fast as humanly possible. Chapter 4, An Engine Looking for an Airplane. The engine in question was the Pratt & Whitney R2800 Double Wasp, an 18-cylinder, twin-row radial already proven in combat aboard both the F6F Hellcat and the Vought F4U Corsair, a genuinely massive, genuinely brutal power plant capable of producing over 2,000 horsepower. On the Hellcat and Corsair, that engine was married to a comparatively large, heavy airframe built for all-around fighting. Range, firepower, ruggedness, carrier durability. Grumman's new project, initially designated the XF8F1, inverted that entire equation. Instead of asking, how big an airframe do we need to carry this engine and everything else a fleet fighter requires, the design team asked, how small can we possibly make the airframe while still safely housing this engine? And what is the absolute minimum everything else we can get away with? The result, when the numbers finally came together, was almost comic in its extremity. The R2800 engine alone weighed in the neighborhood of 3,000 pounds, while the entire empty aircraft built around it weighed only around 4,000 pounds total. In other words, the single engine accounted for something close to 3/4 of the airframe's own empty weight. An engine-to-airframe ratio, unlike almost anything else flying at the time, propeller-driven or otherwise. Every single design decision downstream of that ratio existed to serve one goal: keep that engine's raw power output translating into the fastest possible climb rate, by making absolutely certain the rest of the aircraft added as little dead weight and drag as physically possible. Put the numbers side by side, and the philosophy becomes almost startling. The Hellcat, built around the same basic R2800 engine family, weighed in at roughly 9,000 pounds empty, more than double the Bearcat's empty weight, carrying that extra mass in the form of a larger wing, heavier structure, more fuel, more armor, and more armament, all in service of being a rugged, long-range, all-purpose fleet fighter. The Bearcat's design team looked at that same engine and asked how much of that additional weight could simply be deleted, given a mission that cared about exactly one performance metric above all others. The answer they arrived at redefined what a fighter could even mean. Not the biggest, not the most heavily armed, not the longest ranged, simply the airframe with the highest ratio of horsepower to pounds that a carrier deck could still safely launch and recover. Chapter 5: The Spartan Treaty. What resulted from that obsession reads today less like a fighter aircraft specification, and more like a monk's vow of poverty applied to combat aviation. The wings folded, a mechanical necessity for any carrier aircraft that needs to be stowed efficiently below deck. But rather than adding the weight and complexity of a hydraulic folding mechanism, Grumman's engineers specified a manual folding system, deck crews physically hauling the wings into position using a metal pry bar as a lever, muscle and leverage doing the work that hydraulic fluid and pumps did on other fighters, at the cost of a small amount of added weight nobody wanted to spend. The carrier arresting hook, the device that catches the arrestor wire and brings a landing aircraft to a stop in a few hundred feet of deck, was similarly hand-cranked rather than hydraulically actuated on many variants. One more small mechanical system stripped down to its lightest, simplest possible form. The pilot seat wasn't adjustable. If you were a shorter or taller pilot than the aircraft's baseline dimensions assumed, the Navy's solution wasn't an adjustment lever. It was seat cushions, stacked or removed as needed, because an adjustable seat mechanism meant more moving parts, more structure, more weight, for a problem a few inches of foam could solve for free. And perhaps most tellingly of all, despite a bubble canopy cockpit that turned into a magnifying glass under direct sunlight, baking the pilot inside a greenhouse of superheated plexiglass while sitting on a ramp in the tropical Pacific sun, the Bearcat carried no cockpit air conditioning or meaningful climate control whatsoever. Pilots simply endured it, because comfort was never once weighed against climb performance in any design meeting that mattered. Every ounce spared from crew comfort was an ounce that could instead be spent getting the aircraft to altitude a few seconds sooner. And in the mission this aircraft was built for, seconds were the only thing anyone actually cared about. None of these were oversights. Every single one of them was a conscious, deliberate line item that Grumman's engineers debated, weighed against the aircraft's central mission, and chose to sacrifice on purpose. A hydraulic wing-fold system might save a deck crew a few seconds of manual labor and some sweat on a hot flight deck, but it would also add pumps, fluid lines, and a heavier actuator permanently baked into every single airframe built for the rest of the aircraft's service life. An adjustable pilot's seat might spare a supply officer the minor headache of stocking different cushion thicknesses, but it would add moving parts and structure that existed purely for comfort on an aircraft whose entire reason for being was to weigh as little as mechanically possible. Looked at individually, each trade-off seems almost petty. Looked at together, they describe an engineering culture that had internalized Jimmy Thock's answer so completely that no comfort, no convenience, and no ordinary assumption about what a modern fighter cockpit should include was safe from being questioned. Chapter 6. The silhouette that gave away the secret. The consequences of wrapping such a small airframe around such an enormous engine went beyond weight savings. They physically reshaped the aircraft in ways you can still recognize from a photograph today. That massive R2800 engine needed an equally massive propeller to convert all that horsepower into usable thrust, and the Bearcat's propeller blades stretched over 12 feet in diameter, enormous for such a physically compact airframe. A propeller that large creates an obvious ground clearance problem, spin blades that long close to the tarmac, and you're one bounce away from chewing through your own propeller tips on every takeoff and landing. Grumman's solution was a distinctively tall, articulated main landing gear, engineered to fold and extend in a way that pushed the aircraft's nose noticeably higher off the ground than most contemporary fighters, giving that oversized propeller the clearance it needed to spin freely. The side effect is the Bearcat's now iconic silhouette sitting on the tarmac, nose held high, tail low, an almost eager, coiled stance that makes the aircraft look like it's already leaning forward into a climb before the engine has even turned over. It's a purely functional compromise, born entirely out of the propeller's raw size, and it happens to also be one of the most instantly recognizable design signatures in American fighter history. Chapter 7. A wart's worth of teeth, in a lightweight, free for all the weight-shaving obsession running through every other part of the design. Grumman's engineers did not treat the Bearcat's armament as an area to economize. Early production models carried 4 .050 caliber machine guns, later replaced on subsequent variants by 4 20mm cannon, a genuinely heavy punch for an aircraft this small, capable of shredding an incoming enemy aircraft in the brief window of a single, well-aimed firing pass. The logic was consistent with everything else about the design. An interceptor that reaches its target fast, but can't then destroy it in 1 or 2 passes, has only solved half the problem. Grumman's engineers were prepared to spend weight on firepower, precisely because firepower, unlike crew comfort or adjustable seating, was directly relevant to completing the mission. Later variants also added underwing hardpoints capable of carrying bombs or rockets, giving the airframe at least a nominal secondary ground attack capability from the factory floor. Though, tellingly, this was very much a bonus feature bolted onto an interceptor design, not a role the aircraft's structure or protection had ever been built around. That distinction, a genuine factory-installed ability to carry ordnance, layered on top of an airframe whose actual engineering priorities were still entirely about climb rate and air-to-air performance, is exactly what would make the aircraft usable, if punishing, when the French Air Force found itself with no aerial targets left to intercept a few years later, and reached instead for the Bearcat's underused hardpoints as its only available answer to a jungle war. It had not designed this fighter to fight. Chapter 8. The wings that designed to fall off. Of all the strange, uncompromising decisions baked into the Bearcat's design, none is stranger or more revealing of the design team's priorities than the aircraft's original breakaway wingtips. Grumman's engineers wanted the lightest possible wing structure they could build. But a lighter wing is, all else being equal, also a weaker wing, and a fighter pulling hard, violent maneuvers in genuine air combat needs a wing that can survive extreme aerodynamic loads without folding or shearing off entirely. Rather than simply overbuilding the whole wing to survive worst-case combat stress, the safe, heavy, conventional solution, Grumman's design team proposed something far more radical. Engineer a deliberate structural weak point near each wingtip, calibrated, so that if a pilot ever pulled hard enough to exceed roughly 9 times the force of gravity, the outermost few feet of each wingtip would cleanly and symmetrically detach and fall away, shedding load before the stress could travel further inboard and catastrophically fail the wing's main structure. It is on paper a genuinely elegant piece of engineering logic. Rather than building a heavier wing to survive every possible overstress event, build a lighter wing that sacrifices a small, expendable piece of itself to protect everything that matters. The trade-off shaved roughly 230 pounds of structural weight off the aircraft. A meaningful savings on an airframe already obsessed with every single ounce. It also turned out to be one idea too clever for its own good. In practice, the breakaway wingtip mechanism proved unpredictable rather than reliably symmetric, sometimes releasing when it shouldn't have, and critically, sometimes releasing on only one wing rather than both at once. A fighter that suddenly loses lift from only one wingtip in the middle of a hard maneuver doesn't gently level off. It snaps into a violent, asymmetric roll with almost no warning, and more than one pilot found themselves fighting a Bearcat that had just, quite literally, come apart beneath them at exactly the wrong moment. After a string of accidents traced back to this exact failure mode, later production Bearcats quietly abandoned the breakaway wingtip concept altogether, reinforcing the wing structure conventionally instead. Proof that even inside an aircraft this ruthlessly optimized, there was still a line between brilliant minimalism and an idea too fragile to trust with a pilot's life. Pilots who trained on our early Bearcats, equipped with the breakaway tips, it described a specific, unnerving sensation that came to define the aircraft's early reputation. A hard maneuver near the edge of the flight envelope could end with a sudden bang, a lurch, and a fighter that was now flying and rolling with two very different wings. Investigators tracing the resulting accidents found that the asymmetric separations were not simply bad luck. Small manufacturing variances between the left and right wingtip fittings meant one side reliably tended to let go a fraction of a second before the other, and in a fighter this light and this responsive to control input, a fraction of a second of asymmetric lift loss was more than enough to snap the aircraft into an uncommanded roll before a pilot could react. It's a small, almost forgotten engineering footnote today, but it captures something true about the entire Bearcat program. Grumman was willing to try genuinely radical ideas in pursuit of shaving weight, and just disciplined enough, when the data came back showing the idea didn't work reliably, to abandon it rather than defend it out of institutional pride. Chapter 9. A name and a number that proved the point. Grumman had built a reputation, by this point in the war, for naming its naval fighters after cats, the Wildcat, the Hellcat, and now this newest, smallest, most aggressive member of the family earned the name Bearcat, evoking something compact, fierce, and disproportionately dangerous for its size. It was, if anything, an understatement when the numbers finally came back from flight testing. They justified every uncomfortable seat cushion and every hand-cranked mechanism that had gone into earning them. The XF8F1 prototype could climb to 10,000 feet in a little over 2 minutes from a standing start, a rate of climb that, at the time, outperformed nearly every other piston engine fighter in American or Japanese service, and one that remained genuinely competitive, even against the first generation of jet fighters that would arrive within the following 2 or 3 years. Test pilots who had flown the Hellcat, the Corsair, and even captured examples of Japanese and German fighters came away from early Bearcat flights describing an aircraft that felt less like an incremental improvement and more like a different category of machine entirely, a fighter that seemed to leap off the runway rather than simply take off from it. Jimmy Thack had asked for climb rate. Grumman's engineers hadn't just delivered it. They had delivered a number that, for a brief moment, redefined what anyone thought a propeller fighter was capable of. Chapter 10, Ready, Willing, and Arriving Too Late. By the time all of this engineering brilliance, and its accompanying growing pains, had been worked through, it was already 1945, and the war the Bearcat had been so specifically designed to fight was entering its final, most desperate phase. Kamikaze attacks against the fleet off Okinawa and elsewhere in the Pacific had become the exact nightmare scenario Grumman's design brief had anticipated back in 1942. Waves of aircraft, sometimes with only minutes of radar warning, diving directly at American ships, with the explicit goal of causing maximum damage, regardless of the pilot's own survival. The Bearcat entered fleet service in the spring of 1945, and the first operational squadron, VF-19, began working up for deployment with genuine urgency, fully expecting to be thrown directly into the fight, defending the fleet during the planned invasion of Japan. An invasion every American planner assumed would be the single bloodiest and most kamikaze-saturated operation of the entire Pacific War. The aircraft that had been engineered, argument by argument, trade-off by trade-off, specifically to shoot down exactly this kind of threat, was finally, genuinely ready to do the job it was built for. And then the atomic bombs fell, and Japan surrendered, and the invasion that would have needed the Bearcat's climb rate More than any single moment in the entire war, simply never happened. VF-19 never engaged a kamikaze. No Bearcat ever fired its guns at a Japanese aircraft in anger. In the entire Second World War, the single most focused, purpose-built interceptor design of the propeller era arrived at the exact moment the mission it existed for disappeared entirely. Chapter 11, dethroned before it, ever proved itself, if missing the war by weeks wasn't a cruel enough twist of timing. The next indignity arrived within months. In early 1946, the Navy staged a mock aerial engagement, pitting the brand-new Bearcat, genuinely one of the fastest climbing, most powerful propeller fighters ever built, against the Lockheed P-80 Shooting Star, America's first operational jet fighter. The result wasn't close. The Bearcat, for all its engineering brilliance, for all its obsessive weight-saving and raw power-to-weight ratio, was still fundamentally a propeller-driven aircraft competing against the first wave of a genuinely new form of propulsion, and the P-80 simply outclassed it across the board, faster in level flight, faster in a dive. No propeller disc creating drag and torque effects to manage it all. The exercise made brutally clear, less than a year after VJ Day, that the entire generation of piston-engine fighter design the Bearcat represented, no matter how perfectly optimized any individual example of it might be, was already obsolete. The jet age hadn't just arrived. It had arrived while the ink on the Bearcat's own service introduction was barely dry. Closing the book on propeller fighter development, almost the moment its single finest example had been perfected. Chapter 12, From Interceptor to Bomber, in Someone Else's War. Here's where the Bearcat's story takes its strangest, most ironic turn yet. Retired from frontline U.S. Navy fighter service relatively quickly as jets took over, hundreds of surplus Bearcats didn't simply go to the scrapyard. They went to war anyway. Just not America's war, and not in the role they were built for. In 1951, the United States transferred nearly 200 surplus F8F Bearcats to the French Air Force, fighting to hold onto its colonial territory in Indochina against the Viet Minh. But the Viet Minh had no air force of their own to intercept, no kamikazes, no incoming bomber raids. Nothing resembling the threat the Bearcat had been engineered, from the ground, up to counter. With no aerial enemy to shoot down, the French pressed their brand-new, ultralight, purpose-built interceptors into an entirely different job. Low-level ground attack, strafing and bombing Viet Minh, positions in the jungles and mountains of Indochina. This was, in almost every meaningful sense, the exact opposite mission from the one the Bearcat had been designed around. Every one of Grumman's original weight-saving decisions, the minimal armor, the stripped-down structure, the airframe cut to the bone specifically to maximize climb rate against airborne threats, became genuine liabilities against concentrated ground fire. An aircraft built to spend as little time as possible exposed to enemy fire while racing to intercept altitude was now flying low. Slow, repeated strafing passes directly into the teeth of ground-based anti-aircraft fire, with none of the armor protection that a dedicated ground attack aircraft would have carried. Losses among the French Bearcat squadrons in Indochina were severe, aircraft and pilots paying the price for a fundamental mismatch between design intent and battlefield reality that had nothing to do with the aircraft's quality and everything to do with simply being the tool available when the mission changed underneath it. Consider what that mismatch actually meant in practice, mission after mission. A Bearcat pilot flying fleet defense in the role Grumman intended would spend his entire engagement racing upward, away from danger, using every ounce of that climb rate to reach an attacker, before the attacker reached the fleet. Speed and altitude working entirely in the pilot's favor. A Bearcat pilot flying ground attack over the jungles and river deltas of Indochina had to do the exact opposite. Dive down toward the danger, slow down to aim rockets and gunfire accurately at a target hidden in dense foliage, and then claw back up and away, through exactly the kind of small arms and light anti-aircraft fire that a lightly built, unarmored interceptor had never been designed to survive. Every quality that made the Bearcat a superb fleet defender, its light structure, its minimal armor, its narrow focus on vertical performance over ruggedness, became a liability the moment its mission flipped from climbing away from a threat to diving directly into one. French pilots did not fail because the Bearcat was a poor aircraft. They suffered because Grumman's engineers, quite reasonably, had never once designed against the threat of ground fire, because ground fire was never supposed to be this aircraft's problem. Chapter 13, A Handoff, and a quiet ending. France's war in Indochina ended in defeat in 1954, and as French forces withdrew from the region, the survivors of their battered Bearcat squadrons, some 28 aircraft, according to most accounts, were handed over to the newly forming Air Force of South Vietnam. There, in the hands of a brand new nation's fledgling air arm, the last operational Bearcats continued flying, still doing the low-level strike work France had originally forced onto them, until they were finally retired from South Vietnamese service around 1960. It's a quiet, almost anticlimactic final chapter for a fighter that had been built with this much obsessive, focused engineering brilliance, an aircraft engineered to be the single fastest climbing defender of an American carrier fleet, ending its operational military life a decade and a half later, strafing jungle trails in someone else's colonial war, thousands of miles from the carrier decks it had actually been designed to launch from. Chapter 14, The Second Life Nobody Planned. For if the story ended there, the Bearcat would be remembered, if at all, as a footnote, a nearly perfect design that missed its war, lost to the jets within a year, and spent its actual combat career doing a job it was never meant for. But the very same engineering obsession that made the Bearcat a slightly awkward fit for 1940s and 1950s warfare turned out to make it an almost perfect fit for something nobody at Grumman had ever designed it for: unlimited class air racing. Starting in 1964, the Reno National Championship Air Races in the Nevada desert became the proving ground for exactly the quality Jimmy Thack had asked Grumman engineers for 22 years earlier, in that meeting 19 days after Midway. Raw power-to-weight performance, surplus Bearcats, cheap and plentiful on the post-war civilian market, turned out to have almost exactly the airframe characteristics a dedicated air racer wants. Small, light, aerodynamically clean, built around an enormous engine, already producing far more horsepower than any 1940s design brief had strictly required for carrier defense duty. Racing teams didn't need to reinvent the Bearcat's philosophy. They simply needed to push it further than the U.S. Navy ever had reason to. The most famous of these racing Bearcats, a heavily modified example nicknamed Rare Bear, took Grumman's original obsession to genuinely absurd extremes, swapping out the original Pratt & Whitney R2800 for an even larger Wright R3D 350 engine, producing well over 4,000 horsepower in its most extreme racing tune, output that would have seemed like science fiction to the engineers who first sat down to sketch the F8F back in 1943. Racing a lineage of increasingly radical modifications, through the 1970s and 1980s, Rare Bear went on to set the world speed record for a piston engine, propeller-driven aircraft 528, 33 miles per hour, set in 1989, a record that stood as a testament to exactly how much untapped performance had been baked into the Bearcat's original airframe concept all along. Rare Bear wasn't a lone success story either. It was simply the most extreme expression of a pattern repeated across the entire unlimited air racing scene at Reno for decades. Bearcat after Bearcat found its way from military surplus yards onto the racing circuit, each one clipped, polished, re-engined, and refined by racing teams chasing incremental gains in exactly the metric Grumman's own engineers had chased first: more horsepower per pound, less drag per unit of thrust, every non-essential ounce found and removed all over again by a new generation of obsessive tinkerers who, in many cases, had no idea they were simply rerunning Jimmy Thack's original 1942 design brief for an entirely different purpose. Where the U.S. Navy had cared about minutes to intercept altitude, Reno racing teams cared about tenths of a second around a pylon. But the underlying engineering problem, and the underlying airframe best suited to solving it, turned out to be exactly the same aircraft either way. Chapter 15. The verdict of the pilots. Madrid. Most aircraft with 0 confirmed air-to-air victories. No significant strategic impact on any war it actually fought in. Retired from frontline service within a couple of years of introduction. Might reasonably be judged, on the cold ledger of military history, as a near miss. A brilliant piece of engineering that history simply never gave a fair chance to prove itself. And yet ask the pilots who actually flew it, and a very different verdict emerges. Among the many combat and test pilots who flew the Bearcat over the decades, one name stands out for the sheer weight of his own personal resume. Neil Armstrong, a Navy fighter pilot before he was ever an astronaut, and the first human being to set foot on the surface of the moon. Armstrong, a man who had flown some of the most sophisticated and demanding aircraft and spacecraft in human history, repeatedly named the F8F Bearcat as his personal favorite aircraft of his entire flying career, not the Gemini or Apollo spacecraft that carried him into history, not the X-15 rocket plane he trained on, but a stubby, obsessively minimalist, piston-engine carrier fighter from the tail end of the propeller era. It is, in its own quiet way, the single most persuasive verdict this aircraft ever received. Not a kill count, not a campaign ribbon, but the honest personal preference of a man who had flown almost everything that mattered in 20th century aviation, and still chose the little fighter that never got to fight its own war. Armstrong was hardly alone in that assessment. Generations of test pilots, airshow performers, and warbird collectors who have flown surviving Bearcats since have echoed some version of the same reaction. A machine that feels, even by the standards of modern light aircraft, startlingly eager, an airplane that seems to want to leap into a climb the instant the throttle moves forward. Responsive to control inputs in a way that heavier, more forgiving wartime fighters simply never were. That responsiveness is not an accident or a happy byproduct. It is the direct tactile signature of every gram Grumman's engineers refused to add, felt through the stick by every pilot who has climbed into the cockpit since. In an industry that tends to remember its fighters by their kill tallies and campaign histories, the Bearcat's most durable legacy is instead a physical sensation, the feeling of an aircraft built around exactly one idea, executed without compromise, still detectable in the controls 8 decades later. Chapter 16. The question historians can't stop asking. It's tempting to ask the obvious counterfactual. What if the Bearcat had arrived just 12 months earlier, in time to meet the massed kamikaze raids off Okinawa in the spring of 1945, rather than missing the war entirely? The honest answer is that it likely would have performed exactly as advertised, and the fleet would very likely have been grateful for it. Contemporary test data and the aircraft's later racing pedigree both suggest the Bearcat's climb rate and acceleration genuinely were exceptional for a piston-engine fighter, more than capable of getting airborne, and to altitude faster than most alternatives available to the fleet at that stage of the war. A handful of additional minutes of warning, converted into altitude advantage by an aircraft this specifically optimized for exactly that conversion, could plausibly have meant a meaningfully higher interception rate against incoming raids during the war's bloodiest final months. But the deeper, more interesting counterfactual isn't really about timing at all. It's about mission permanence. Even in a world where the Bearcat arrives a year earlier and flies a full combat tour against kamikazes over Okinawa, its window of relevance would still have been almost comically brief. The jet age was arriving regardless, on almost exactly the same short timeline. The Bearcat wasn't unlucky merely in missing one specific war. It was unlucky in being the last, most perfected expression of an entire category of aircraft that the wider arc of aviation history was retiring at that exact moment, almost regardless of what any single squadron did or didn't accomplish in the closing weeks of 1945. There's a second counterfactual worth asking too, quieter but arguably more poignant. What if the Navy, seeing the P-80's clear superiority in early 1946, had simply scrapped every Bearcat in inventory, rather than letting hundreds of them linger in storage long enough to be handed to France 5 years later? In that version of history, the aircraft's combat legacy ends exactly where its wartime story ends. An interceptor that never intercepted anything, retired quietly and completely forgotten outside of enthusiast circles, never given the chance to be misused over Indochina, and never given the chance, decades later, to be rediscovered by racing teams in Nevada. It is a strange thing to sit with. The Bearcat's most painful chapter, flying low over jungle tree lines under a mission it was never built for, and its most triumphant chapter, screaming around desert pylons. Decades later, both exist only because the aircraft was allowed to linger in surplus inventories rather than being quietly scrapped the moment the Navy decided it was already obsolete. Sometimes an aircraft's afterlife turns out to matter more than its intended service ever did. Chapter 17. The ultimate paradox. Step back now and look at the whole shape of the story we've just walked backward through. The United States Navy asked a blunt, specific question of its most experienced combat pilots 19 days after one of the pivotal battles of the Pacific War. Got a blunt, specific answer and built, with genuine engineering brilliance and near-obsessive discipline, one of the most perfectly optimized propeller fighters ever to fly, an aircraft whose every design decision, down to the seat cushions and the intentionally breakable wingtips, existed in service of a single number. How fast can this airplane reach altitude? And then history simply declined to give it the war it was built for. It missed its intended enemy by weeks. It was outclassed by an entirely new form of propulsion within months. It was handed off to fight someone else's war, in a role its own designers had specifically engineered against. And it paid for that mismatch in lost aircraft and lost pilots over the jungles of Indochina. And then, decades after the Navy had stopped caring what a piston fighter could do, this same airframe found its actual moment of glory, not defending a fleet, not winning a war, but screaming around pylons in the Nevada desert at over 500 miles an hour, setting a world record that stands as proof of exactly how much performance Grumman's engineers had built into it all along. The fighter that never fired a shot at the enemy it was designed to kill ended up being remembered by the men who actually flew it, including a man who once looked back at Earth from the surface of the moon as simply the best airplane they ever got to fly. Sometimes the truest measure of a machine isn't the war it fought. It's the war it was ready to fight, the genius poured into making sure it could, and the strange, scattered, unpredictable places history eventually finds for that genius to finally prove itself, even if none of those places are the ones anyone originally intended.